Good day, viewers and students. So today we will be discussing about a certain topic on structural theory. It is called approximate methods and shears for continuous beams and one-way slabs. It could be found in NSCP 2010 408.4.3 and the latest version of the National Structural Code of the Philippines in 2015 406.5. Okay. Okay, so let's proceed. Okay. So this is from 2010. Actually, it is um, NSCP 2010. So in 408 4.3, it is this is mentioned approximate method, which is adopted from the ACI code or the American Concrete Institute. Okay. As an alternate to frame analysis, the following approximate moments and shears shall be permitted to be used in design of continuous beams and one-way slabs. Okay. Speaking of one-way slabs, those are slabs reinforced to resist flexural stresses in only one direction, provided that there are two or more spans. Spans are approximately equal, with the larger of the two adjacent spans not greater than the shorter by more than 20%. 3. Loads are uniformly distributed. 4. Unfactored live load L does not exceed 3 times unfactored dead load D, and the fifth and the last members are prismatic. Okay, so these are the 5 main criteria in order that we can apply this type of approximate methods. Mainly, this type of method is basically applicable to non-prestressed beams and one-way slabs. Okay, specifically prismatic. When we say prismatic, it has something to do with rectangular cross-section area. Okay, so if your cross-sectional area is prismatic, it could be from the root word prism, which means it could be discerned that it should be uh, a rectangular type in its cross-sectional area. So if that is the case, we can apply this method. Okay, so for calculating negative moments, okay, Ln is taken as the average of the adjacent clear span lengths. For positive moment at end spans, okay, under end spans there are 2. For discontinuous and restrained, WLN squared over 11. For discontinuous and integral with support, you can use the formula WLN squared over 14. For interior spans, WLN squared over 16. For negative moment, at exterior face of first interior support, if the continuous beams or slabs is in 2 spans, you can use WLN squared over 9. If it has more than 2 spans, you will use WLN squared over 10. At other faces of interior supports, you will use WLN squared over 11. At face of all supports for slabs with spans not exceeding 3 meters and beams where ratio of the sum of column stiffness to beam stiffness exceeds 8 at each end of the span, you use WLN squared over 12. At interior face of exterior support for members built integrally with supports, there are two types. If the support is a spandrel beam, you use WLN squared over 24. When the support is a column, you use WLN squared over 16. Okay, let's proceed. For shear, there are only two formulas you need to remember. If we refer to at a face of first interior support, the formula for shear is equivalent to 1.15 WLN over 2, and at the face of other supports, you will use WLN over 2. Okay? So to clarify all those terms, let us consider this drawing. Okay? So as we can see, this drawing is composed of columns and beams. Okay? So if this is your columns and beams, logically, your exterior support are those columns or other supports that exists at the outside, okay, at the edgemost. Okay, this is the exterior supports which could be found on the farthest end of the frame, or uh, of the of what we are column beams we are referring to. So these are the exterior supports, and next we have the interior supports. If the exterior supports are those supports that exists on the farthest ends, the interior supports are those inside, okay, other than the exterior supports. Those are the supports, intrinsic supports, or that can be found inside, other than the farthest ends. So it is found in the middle. Okay, those are the supports that can be found in the middle. So that is interior support. And then we have the exterior span. Okay, so if we have the exterior and interior supports respectively, we also have the exterior span. When we talk about exterior span, those are the spans, okay, on the farthest ends. Okay, so this is the exterior spans, and other than the exterior spans, the rest are the interior spans, which can be found in the middle. Okay, exterior span and then the interior span. Okay, speaking of bending moments, these are usually the form of bending moments, or simply called as moments in a continuous beams. Okay, speaking of signs, those found at the top. Okay, so we draw the bending moments of these for each of the beams in this figure. So the positive side are located at the middle. Okay, and the negative signs are found at the edges. Okay, so at the middle, it's positive. Okay, and since it is found at the top, it is positive. Okay, this is positive and this is positive, and those near near the supports, either in the exterior or interior sides of your supports, okay, those intersecting the supports, the signs of those moments are negative. Okay, okay. So then, for shear forces, uh, um, those this is for this in this form of shear force diagram, this is positive, and uh, those under the beam is negative. So at the top of the beam, the shear the sign is positive, and at the bottom of the beam it is negative. So this is for bending moments and shear forces respectively. This is the common form of its um, diagrams. Okay, just remember the sign convention, where you could find the positive and then where you could find the negative. Okay, so since this is a video, you can repeat. Okay, you can rewind the portions of this video in which um, is not clear to you. Okay, you can revisit this anytime you want. Okay, so this is the bending moments and the shear moments, the form, its common form and its sign convention. Okay, so let's proceed. So speaking of, there are terms that we need to know in order to understand how to solve, um, how to use this approximate method. Okay, so we have interior face of exterior support. So since we know that this the farthest ends are the exterior supports, and then there is an and the rest in the middle is the interior supports. Okay, so we have this term we call first interior support. So if this is our exterior supports on the farthest end, the first support adjacent to that exterior support is the first interior support. Okay, so the first interior, so if this is your exterior support relative to this is your first interior support, and from this exterior support, this relatively, this is your first interior support. Okay, speaking of exterior and interior face, so this side is the interior face of your exterior support. Okay, so this is your exterior support, so this is interior face. Okay, and then since this is your first interior support, this is your exterior exterior face of first interior support. So as this on our right side, this is the interior face of your exterior support, and this side is the exterior face of your interior support, and all the faces inside are what we call the other faces of your interior support. Okay, so this is for a 4-span uh, continuous beam. Okay, so this is your continuous beam. It is supported by 5 columns or 5 supports. So this automatically, those at the farthest ends, those supports are called exterior supports. And the first support adjacent to your exterior supports on both sides are the first interior supports respectively. So this is first interior support, and this is your first interior support. And then other than the first interior support, the rest of the interior supports will be called other interior supports. Okay? Since this is your exterior support, this will be the interior face of your exterior support, respectively, on both sides. And then we have exterior faces of your interior supports, which located in these areas. Okay, and the other faces, okay, and the rest of the faces are the other faces of interior supports. Okay, so we can use okay. Okay, so let's have some examples. Okay, for two span continuous beams. Okay, so this time we will be tackling um, the applications of NSCP 2010 408 408.43 point 4.3. Okay, so speaking of this, okay, speaking of these terms, okay, so in order to simplify that, we have some example drawings. Okay, so let's proceed. So this is for two span continuous beam. So you have let us say you have a uniform load. Okay, so the WU is the uniform load. Okay, supposed to be this WU should be equal in all the spans, of beams. Okay, so you cannot use this type of approximate method if the WU of this span and the WU of this other span is not equal. Okay, so please bear in mind that all these spans should have an equal value of WU. Okay, speaking of, so let us consider that the lengths of those spans. Okay, so I would like to clarify that the spans we will be using in this approximate method should be the clear span. Okay, when we say clear span, it is from the inner edge of your columns. Okay, so do not use the distance, the length of your beams center to center from your columns, but the inner span. Okay, the inner edge of your column supports, or in some cases there might be cases that girder support. Okay, it should be the clear span. Okay, speaking of relative to these two span continuous beams, let us choose, we can choose what is applicable in this situation. Okay, so since, okay, for positive moment, for the end spans, since it has two end spans, okay, these are, both of these are end spans, okay, or exterior span. Okay, when we say exterior span, end span, it is also called exterior span. So here, okay, so here for the end spans, it has a discontinuous end integral with support. Okay, we do not use this discontinuous end unrestrained. Okay, we have discontinuous and integral with support because it has supports. So for that, we will use WU ln squared over 14. And then, okay, sorry. For a negative moment, so at exterior face of the first interior support, okay, for two spans, since we have two spans, we will use WLN squared over 9. And then at the interior of the interior face of exterior support for members built integrally with supports, since the support is column, we will use WLN squared over 16. And for shear, in all types of spans, or in all types of continuous beams or non-continuous beams that would be applied by this formula, we use this. At face of first interior support, we will use 1.15 WLN over 2. And at the face of other supports, WLN over 2. Okay? So this is it. Okay? So since this is the at okay, at this side, this is um the interior face of of the exterior support. Okay, speaking of end span. Okay, this is the okay, so this is the interior face. Okay, speaking of interior face of exterior support, so we have WLN squared over 16 on both sides. Okay, and then for the positive moment, which is located at the middle, the discontinuous end integral with support is WLN squared over 14. So here. And then, the exterior face of your first interior support, so since this is our first interior supports relative to the exterior supports, okay? So, at that point, you use, since it is 2 spans, WLN squared over 9. So, that's why we use WLN squared over 9. And then, please take note that there are two, you should remember two rules in order to compute your LN. So, please remember, for computations of positive moments, take the length of the beam span as Ln, okay? And then, for computations of negative moments, take the average of two adjacent spans as Ln, okay? So, it's different when we compute the positive moments and the negative moments. For computation of positive moments, we take the length of the beam span, or other term, if it is a one-way slab, we use the length of that, or the span of that beams or slab as Ln. But for negative moments, we take the average of two adjacent spans as Ln. Okay, so in order to understand that, okay, so consider this figure. Okay, so since this is L1, this has a clear span of L1, and this beam has a clear span of L2. Okay, so automatically, since this negative moment at its exterior, at its at exterior side of the beam, since it has no adjacent length, so its length is just L1. Okay, so from this figure, okay, from this figure, WLN squared over 2, its length will be L1. And since this is a positive moment, we automatically use the length of this span, L1 squared over 14. And since this is your interior support, and this is an interior negative moment, so we take the Ln as the average of the two adjacent spans, in which this interior column is in between of these two spans. Okay, so this is the left span and the right span. You average that one, that will be the Ln of your interior negative moments. So both in this side and this side. Okay, so take it as the average of these two adjacent lengths. And since these are positive moment and this is exterior negative moment, you just take the length of the span directly, okay, of the clear span. You use L2 squared over 14. Also for this exterior negative moment. Okay, so I hope we understand. So we proceed. So for two spans, continuous beams, okay, so please remember that we have for exterior, okay, for exterior, for the faces of the interior support. So since this is our only interior support, first interior support, all of its shear is equivalent to 1.15 WLN over 2. But since we have L1 over L1 and L2 respectively, we use LN, we take LN as the span, okay, as the span of the shear, as the span, okay. So those adjacent, okay, the adjacent formula is only applicable for bending moments, but for shear forces you take directly the length or the length of the beams to replace the ln in the general formulas. Okay, so this is it, WL1 over 2 at the exterior shears, and for the interior shears of the first interior support, the 1.15 WL2 over 2. Okay, but okay, so for 3 span continuous beams, okay, so we still have uniform load W U, and we have a clear spans of L1, L2 and L3 respectively. Okay, so we pick up which formulas is applicable in this situation for 3 span continuous beam. So we have N spans, and this under that we have discontinuous and integral with support. Okay, so this is your discontinuous end. Okay, so when we speak of discontinuous end, we speak of the end spans. Okay, so end span and discontinuous end are the same. Okay, so WLN squared over 14, and for interior spans, that is WLN squared over 16 for when computing positive moments. For negative moments, since we have more than 2 spans, okay, so at exterior face of first interior support and it has more than 2 spans, we use WLN squared over 10. And then for the other faces of interior supports, we use WLN squared over 11. And then at the interior face of exterior support, for members built interiorly with supports, okay, since this is a column support, it is, okay, we use WLN squared over 16. And then for the shear, it's the same. At the face of first interior support, we use 1.15 WULN over 2. And at the face of other supports, we use WULN over 2. Okay? So this is the general formula. Okay? So if we use 3 span continuous beams. Okay? So we all know, because this is the exterior span or the end spans. So at the end span, the positive moments are WLN squared over 14 respectively. And at the middle, okay, of the interior span, we use WLN squared over 16. Okay? So for the exterior face of first interior support, so this is the exterior face. Yes, this is the exterior face of the first okay, so this is no, this is the exterior faces of the first interior support. So it is said that it should be WLN squared over 10. That's why, okay, we use this. Okay, so this is the first, so these two are the first are the exterior, okay, interior face. Okay, so this is your interior support. Both of these are the first interior support, since this is exterior support, and relative to that, you count, okay, because this is adjacent to this exterior support, this is first interior support. And since this is also an adjacent support to an exterior support, which is this is also a first interior support, and this is its exterior faces of each of that interior support. So we use WLN squared over 10 respectively according to this table. And then at the other interior supports, we use WLN squared over 11. Okay, so that one according to this. Okay, and then we have interior face of exterior supports for members built integrally with supports. Okay, so this is the interior face. So these are the interior faces of the exterior supports as mentioned in this table. Okay, so we use WLN squared over 16. And since we all know that for exterior negative moments like this 2, and for all the positive moments like this and this 3, we use directly the length of the span. But for the interior, okay, for the interior negative moments, just like this 4, 1, 2, 3, and 4, okay, so we average the two adjacent lengths. Okay, that's why L1 plus L2 over 2, and then for this side L2 plus L3 over 2. Okay, so we proceed. So these are for 3-span continuous beam. So this is how you compute the shear forces. Okay, so these are the shear forces. So WL1 over 2. So this is the shear force on this side. So this is positive, and then this is negative. Also for this positive, negative, and negative. Okay, so I did not include the sign convention yet, so that you will not be confused with what is mentioned in the tables. Okay, so since this is your first interior support, and then it is said, okay, it is said that at the face of first interior support 1.15 WUL n over 2. Okay, so we identify that this is your interior support. So at the faces, which means this both of this and this one and this one, since they are both interior supports, these are the faces. So we have the coefficient of 1.15. Okay, that 1.15, you multiply it by WU times the length of the span over 2 respectively. Okay, so that is only applicable to the faces of your first interior support. The rest will be WUL1 of WULN over 2. Okay, so this we use L3. So supposed to be this is L3. Okay, sorry. So suppose this is L3. Okay, may I correct myself. Okay, so this is supposed to be L3. Okay, L1, L1, L2, L2, L3, L3. Okay, so this refers to the clear spans. Okay, please do not forget about that. Okay, maybe many of you will use, instead of clear spans, you will use edge to edge or center to center. No, it should be the clear span. Okay, so let us continue. So what if we have 4 continuous beams? Okay, 4 span continuous beams. So it has 4 span. So we also have a distributed load of WU, and we have L1, L2, L3, and L4 respectively. So what we should do in this situation, okay, so again we refer into the table. Okay, so we have for end span, okay, so we choose what is applicable. So since for end span, discontinuous and integral with support, we can use WU L squared over 14. For interior spans, the same, WL n squared over 16. And then since it has more than 2 spans, we use WLN squared over 10, WLN squared 11 for other faces of interior support, and then for interior face of exterior support, since it is supported by columns, we use WLN squared over 16. Okay, same uh, same use for shear. The face of first interior support is 1.15 WLN over 2. And for all other faces, for all other supports, we use WLN over 2. Okay. So this is for bending moments. So since, as mentioned, for discontinuous and integral with support, okay, for end span, speaking of end spans, this is we use WLN squared over 14 for this positive moment at the exterior sides. And for the interior support, for the interiors, we use WLN squared over 16. And okay, so maybe the best the technique that we would advise is um, uh, please, okay, is you do first the positive moments before the negative moments. Okay, 14 over 14 for the exterior sides and over 16 for the interior sides. And then we have, since we have more than 2 spans, the exterior face of the first interior supports. Okay, exterior face of first interior support. So this is your first interior support. Okay, these two respectively. Okay, first interior support, since this is the first adjacent support to this exterior support, and this is also a first interior support. Okay, and then the exterior side of this one is this and this. So according to the table, it should be WLN squared over 10. So we use this. Okay, and then for other faces of interior supports, we use WLN squared over 11. That's what. Okay, that's why. Okay. Okay. So here we are again. So since for the rule of computing the LN, so we use directly the clear span of the beam when computing for the positive moments and for the exterior negative moments, since the exterior negative moments has no adjacent side other than the end spans. But for the middle for the negative moments at the interior supports, we need to average the two spans. Okay, so concentrating at this interior span, so this negative moment, its ln should be the average of this one and this one. Also for this for the right side, okay, this one, we should average L1 and L2. And for these two sides, we need to average L2 and L3 respectively in order to compute this negative moment at the left side of this interior support and this one. also we need to average L3 and L4 respectively to compute these negative moments at each side of this interior support. Okay, so I hope we understand each other. Okay, this is for shear forces again. Okay, so this is your first interior support. Okay, so in order that you will have no difficulty, so concentrate first on the first interior support. So this is your exterior support, this is your exterior support. So there, because these two are your exterior supports, the first interior supports are this column and this column. Okay, and this column at the middle will be your other interior column. So the one with 1.15 WN L over 2 are those at the faces of the first interior supports only. So this one and this one should have the coefficient of 1.15 WLN over 2 respectively. These two only, and the rest will be WLN over 2. But please take note that in computing the shear forces, you can use directly the clear spans of each of the beams. Okay. Okay, so another one. So these are for the two span with one end supported by girder or spandrel beam. Okay, so not all that time that in a building frame that the beams will be supported by columns at all sides. Sometimes a beam can be supported by another beam. So it can be supported by a girder beam or by a spandrel beam. So if this is the case, we have the distributed load WU and L1 and L2 respectively. Okay. So we can use this, okay? Positive moments, okay? So speaking, we go again to the table. We have end spans, discontinuous, and integral with support. We use WLN squared over 14, okay? Since it has both exterior loads only, it has no interior spans. Okay, this is exterior span and this is your exterior span respectively. Okay? So the exterior face of first interior support, we have WLN squared over 9. And then since it is supported by a spandrel beam, so at interior face of your exterior support, you use WLN squared over 24. Okay? Same, the rule for the shear is uniform. So it's still the same. So that's why, okay? So at this side of girder beam, okay? So please take note, no? Remember your two span continuous beams. The only difference is that on this side you use WLN squared over 24 in computing the bending moments. Okay? So the same, you compute the for the positive moments and the exterior negative moments, you use directly the span. Okay, you use directly the clear span. But for the interior negative moments, you average the two adjacent spans in order to get your LN. Okay, so same. Okay, sorry, I need to. Okay, so these are for the shear forces. Okay. Okay, so these are for the shear forces. Okay, so it's still the same. Okay, whatever the form of your continuous beam or continuous slabs, you use the same formula in which your first exterior beam will be 1.15 W L N over 2. And for the other faces of other supports, you use W U L over 2. Okay, it's still the same. Only the moments is not the same. Okay, so for this one, 2 spans with one end unrestrained. Okay, so may I, okay, okay, so let's same method, we go again to the table. Okay, okay, so I will explain. Okay, so when we say unrestrained, so one side is free to move. Okay, so since it is unrestrained, it could be a ruler or it could be a rocker type, in which uh, at this side it would allow some displacement. So if that is the case, okay, okay, speaking of positive moments, okay, so discontinuous and unrestrained. Okay, so for positive moments, um it's the formula for its moment is WLN squared over 11, in contrast with end integral with supports, which is WLN squared over 14. Okay, same with negative moments, since it has two spans, you use WLN squared over 9. And since, okay, so I'm sorry, so okay, so this is not a spandrel beam. Okay, okay. So okay, sorry. So since, okay, so this is since we use column at the other side, okay, this side. So we use where support is in column. Okay? So we use, so the only difference here with uh, two spans of continuous beams is at this side, since this is a ruler, it could not absorb any uh, moments, or since it is unrestrained, for an unrestrained end, it should have a zero moment. And since we have new rule for discontinuous and unrestrained, the positive moment at that side, on this one, should be WLN squared over 2. Okay, unlike for, if it is discontinuous and with support, you use WLN squared over 14 for that positive moment. And again, use WLN squared over 16 on the exterior, okay, on the interior face of your exterior support. Okay, so this one, because it has two spans only, both of these are exterior or end spans. Okay, so this is for your bending moments. Okay, so same rule apply. The positive, for computing the positive moments, your ln will be automatically equal to the span. And for the exterior negative moments, but for the interior negative moments, you need to average the two adjacent sides, in which the support is in between of. Okay, so this is your interior support, this is your adjacent lengths. Okay, so you use this on both sides of that, in order to you use that, the average of L1 and L2 over, in order to compute the negative moments on both sides of this interior support. Okay, so that is how it is solved. Okay, so I am always repeating this so that you will always remember also. Okay, so same, this is not bending moment, this is shear forces. Okay, sorry. Okay, so same rule will apply. So only the moments is rigid, okay, is difficult to relatively difficult to use, but for computations of shear forces, um, same rule will apply. You only look for the first interior support, since this is a support, okay, although it is unrestrained, and this is your exterior support, so this is your interior support. So this will carry the 1.15 WN WU over 2 respectively, okay? And for the other sides of the supports, you use WU over 2, okay? So for computing the shear, again, I repeat, you use directly the length of the spans, okay? So since this is the length of your beam, L1, you use L1 to compute the shears on this one, on both this. And then since this is L2, you use this directly in order to compute the positive and negative shears forces on this one. Okay? So that is how it is. Okay? So this is again another case. What if we are using one-way slabs with spans less than 3 meters? Or again, what if the sum of the stiffness, okay, this is also applicable if the sum of the stiffness of columns divided by the sum of the stiffness of beams at each face is greater than or equal to 8. Okay? Just like this. Okay? So all faces of supports for slabs with spans not exceeding 3 meters and beams where ratio of sum of column stiffness to beam stiffness exceeds 8 at each end of the span. Okay? So if that is the case, you use this. Okay? WLN squared over 14 for discontinuous end integral with support, o speaking of positive moment, and for interior support, the positive moment again is WLN squared over 16. And the rest of the negative moment will be uniform at WLN squared over 12. Okay, and again, same, the rule is uniform for computation of shear forces. Okay, again, since these are the end spans, so the positive moment is WLN squared over 14. And for the interior spans, the positive moment is WLN squared over 12. And for the, since this is one-way slab, if it with spans less than 3 meters, so therefore, all of your negative moments, whether it is in exterior or on the interior side, as long as it's negative moments, you use the formula WLN squared over 12. And then, again, please remember that for the computations of positive moments, take the length of the beam span. Okay? Beam span or the span of the slab. Okay? The clear span. And for the computation of negative moments, take the average of two adjacent spans as ln. Okay? Same will apply. So for this one, ln, you use the average of L1 and L2 for each side of this support. For this support, and then same will apply to the other interior supports in the computation of their each negative moments on each side, whether left or right side. You take the average as long as it is the negative moments on the sides of the interior support. Okay, so I hope we understand each other now. Okay, so this is for shear forces again, and again I will remind you that the only thing that is different in computing the shear forces is the first interior support. So since this is the exterior supports respectively, these are your first interior supports. and each of its phases, the shear forces will be computed as 1.15 WU ln over 2. And then the rest will be W L over 3 over 2 for the rest of the supports. Okay? The only thing that is different, that the shear will be computed differently, is the first interior supports, which are these. Okay? This one and this one. W 1.15 WN L over 2, and the rest is WLN over 2. Okay? So that is how we use the approximate methods, okay? Approximate moments and shears for continuous beam and one-way slabs. Okay? So I hope you understand now. Okay? So since this is a video, you can revisit and rewind this video. Okay? To what portion you did not understand, you did not that is not clear to you, so you can rewind this anytime of the day, anytime you are convenient. Okay, so and please do not hesitate to ask in the comment section if there is something that is not clear to you. Okay, so thank you for listening.